Good afternoon,
sir. Good afternoon, people. So, hope you've been trying out the questions from rotational mechanics, especially yesterday. So, any other doubts from HC Verma? Okay, did you go through the questions we discussed yesterday?
Yes.
Okay, now there are few questions that I want to discuss myself from HC Verma. In case you have not tried out these questions, you can just let me know. Okay. And also, if you have any doubts of your own from HC Verma, please text it to me or just tell it to me. I'm going to discuss that now. So I think we had done up to question 37 yesterday, right? Okay, now I want to discuss question 41. If anybody has a doubt in particular in that question, we can. Okay, Harsh, I've got your message. I'll come to question 44 also. Just want to start with this question number 41.
Okay.
Okay, so what's happening in this is that it says there's a uniform ladder of length 10 meters, mass is given, resting against a vertical wall, making 37 degrees with it. Wall is frictionless, ground is rough, and there's an electrician or basically a person weighing 60 kgs. He stands on the ladder at 8 meters from the lower end. What will be the normal force and the frictional force by the ground? What should be the minimum coefficient of friction? Okay. So I'll make the diagram straight away and explain the question. So imagine this is the interface between a smooth wall and a rough floor. So this is frictionless. This surface has some coefficient of friction. And now we have placed a ladder which has, so the side of a ladder will just look like a rod or a stick like this. So we placed a ladder which has some weight of its own. But apart from that, there's also a person standing on the ladder. This ladder has a mass of 16 kilograms and a total length of 10 meters. And it is resting such that it makes an angle 37 with the wall. So this angle is 37. On this, there's a person standing. And let's say that person's mass is capital M. So that is 60 kilograms. And he is standing at a position such that his distance from, he's on the ladder at a point which is at a distance of 8 meters from the point of contact on the floor. 8 meters from the lower end. So it is not a height of 8 meters, but rather it is at a distance of 8 meters along the ladder from the lower end. So we have to find the normal reaction and friction at the floor and the minimum coefficient of friction required for the system to be at rest. So this comes in the category of problems which is called static equilibrium of rigid body. Okay, so what we can do is we can treat the ladder as an object, like a rigid body, and just show all the external forces acting on it. And since it is in equilibrium, so net force should be 0 and net torque should be 0. So on the ladder, how many forces are acting? Can you tell me? What is the total number of forces?
Sir, two normal reactions.
Yes, very
One
good.
That person's weight.
Person's weight, yes. Person's weight will be like a reaction force.
Yes.
Now, what is the direction of normal reaction at the wall? Can you tell me?
Sir, horizontal.
Horizontal, yes, because the contact surface is the vertical wall, so the contact force should be normal to it. Okay, so the plane of contact is vertical, so the force is horizontal at this corner point. So let us say that is n prime. Okay, and then there is the person's weight, which is acting like a contact force itself, or like a reaction force. You can say R, and that will be equal to mg. Okay, now one more force will act. Can you tell me what that one is?
Sir, friction.
Yes, and what should be the direction of friction?
Horizontal. Left side.
But left side. Yes, very good. Because you can see n prime is towards the right. So if the net horizontal force is 0 on the system, the friction has to be 0. So these are all the forces which are acting, and the system is at rest. Okay. So now what we have to do is we have to solve for the condition of equilibrium, that net force is 0. So take along the horizontal, so we have friction balances n prime, and along the vertical, we have n balances r plus small mg, or n is equal to capital Mg. Okay. So capital Mg plus small mg. Okay. So we have how many unknowns? We have friction, normal reaction, and the other normal reaction n prime. We have 3 unknowns. So we also need the torque equation. The net torque should be 0. Okay. Now what point should we select for balancing the torque? See, this is the center of mass of the rod.
Yes.
This is the point where the person is standing. So it's at a distance of 8 meters from below. This point is, let's say, one end of the rod. This point is another end. So first of all, tell me, is there any restriction that I have to take a particular point to balance torque, or can I take any point I choose?
So center of.
Is there a restriction that I have to take center of mass? No, no, because I'm balancing the torque. No?
Yes.
See, there's no rotation happening about any axis. Neither there's rotation about center of mass, nor there's rotation about any other axis. No? The body is at rest. So now it is a arbitrary decision. Like we can arbitrarily choose, or we can choose at convenience whichever point we like to balance it on. So yes, center of mass will work. We can always balance about the center of mass, but there is no hard and fast rule here when there is equilibrium that we have to select that center of mass. So we can take about any axis of choice. Okay. So if I'm considering any axis, which is the most convenient axis, is going to be the one where maximum forces are acting, because they will not count for torque. So most convenient will be about A, about the point of contact at the floor. This point is clear to all of you?
Yes.
Okay, so about that point of contact at the floor, you can see we don't have to consider the two forces A and N then. We have to only consider these other forces, mg of the rod, which is acting through the center, then this reaction force kind of thing, capital Mg, which is acting through the point P, and this normal reaction, N prime. The other two forces I don't have to consider. Okay. So now about this point A, you can see what all is creating clockwise torque. R and small mg, they are creating clockwise, and N prime is creating anti-clockwise torque. Okay. Now for this one, how much will be the moment arm? Okay, so if this distance is, we know the distance AP is 8 meters. Okay. So the moment arm for this R wala force, let's write this as X1. So X1 will be how much? It will be, this angle is theta with the vertical. So X1 will be AP cos theta. Is that correct? And theta is
Yes.
37. So cos 37 is how much? It is 4 by 5. X1 is this much. Similarly, for the other one, small mg, the moment arm will be this distance. To drop the perpendicular, this distance is x2, let us say. So CA, that distance is 5 meters, half the length of the rod. Okay. So x2 is again becoming, oh wait, I have made a mistake now. It should be sine theta, not cos theta. Because theta is this angle now, not the angle with the horizontal, it's the angle with the vertical. So it should be AP cos theta, and theta is 37. So the value was correct, 4/5, but I had written it wrong, I think. Okay. So x2 is now how much? It is 5 sine theta. Okay. So again, sorry, what's happening? Written it wrong twice. Should be sine 37, and therefore it should be 3/5. Okay. And this should also be 3/5. This should be my x2. Okay. Whereas for n prime, what is the moment arm? This is a line of action. So this is the moment arm for n prime. So let's say this is y1. So y1 is how much now? It is L cos theta. Y1, if this point is B, is AB cos theta. So that is 10 into cos 37, which is 4/5. So y1 is 8 meters. Okay, x1 is 24/5 or 4.8 meters. Okay, and x2 is 3 meters. Okay, so are the calculations clear of the moment arms?
Yes, sir. Clear.
I hope this is clear. People understood now. We are taking the axis through A. So for each force, the torque is force multiplied by moment arm. So we have to draw the line of action of the force and find the perpendicular distance. So for R, it is this vertical line through P. For mg, small mg, it is the vertical line through C. And like that for n prime, it is a horizontal line through the point P. So these are the perpendicular distances, x1, x2, and y1, and this is how we have calculated them. So now when we do the torque balancing about A, the torque due to mg plus the torque due to R, both of which are acting anti-clockwise. That has to be balanced by the torque due to n prime, which is acting clockwise. So now you just express the torque in terms of force into momentum. So this x2 in my diagram, R into x1, and this should be equal to n prime into y1. So small mg was how much? It was 16 kg. So 16g into x2, which is 3 meters. Okay. Plus R is the weight of the person. So R is capital Mg, so it is 60g. So plus 60g into this thing, 4.8 meters. This should be equal to n prime into y1, and y1 we just saw is 8 meters. So this third equation is directly going to give us the quantity y1. Okay, and then sorry, the quantity n prime. And then we know the quantity capital N from here. We'll know the quantity friction by substituting n prime from here. Okay. So this is becoming how much now? Becoming 48 into 1 plus 6 na? G divided by 8. So 42G. Just check my solution. Okay. So n prime is coming out to be 42G. Okay. The combined weight is how much? It is 60. So it's fine. It will be around this range only. So n prime is this. Now from equation 1, you can see the amount of friction acting, which is static at the floor. It is n prime equal to 42G. Whereas from equation 2, you can see that the normal reaction at the floor is the combined weight. So the combined weight is how much now? It is 16 plus 60. So that's 76 G. So this friction that is acting should be less than equal to mu n. So mu should be greater than equal to. So the minimum value of mu is equal to this ratio. 42/76, the ratio of this. So mu should be greater than equal to this. So just go through this carefully once. Let me know if there's any doubt with the equation solving and that. Let's check the answer for you. Okay. So this is one of the reasons I wanted to discuss the question, that Remember that we are not obliged to balance the torque about the center of mass when the object is a stationary object, when it is in equilibrium. We can balance torque about any axis of convenience. Okay. So that is something which will help you solve these type of problems more efficiently. Static equilibrium problems. Okay, so people hope this question is clear. Now we will move on to Harsh, question number 44, which you asked. 44 is also an equilibrium problem, but it's a little bit more tricky. Okay. Because how the forces act is not so straightforward in 44th question. So we will just discuss. So you have this door. Just think of it like a rectangular plate. Okay. So its length is given to us, it's 6 feet or whatever. Its width is given to us, it's 1.5 feet. And its mass is 8 kilograms. Now here's the interesting thing. It's supported by two hinges. So there's one hinge here, right? That is H1, and another hinge here, H2. And each of the hinges is at a distance of 1 feet from the end. So if I write this distance as D over here, this is 1 foot. Same this distance. Okay. And it is also given that the reaction force at each hinge H1 and H2 are of same magnitude. Now this actually becomes an essential part of solving the question, and we'll understand in a bit of time how we'll make use of this condition. Right, so we have to find this magnitude. So we have to find this reaction force's magnitude. Okay, so H1 and H2 are the hinges. Okay. Now, can you give me an idea about what should be the direction of reaction force at each hinge? Any thoughts about that? So just imagine what is happening at the hinge. It's like the door has some part which is, something like a slot that is attached to it, and that slot is fixed to the wall and it can rotate about that slot, that kind of thing it is at the hinge. So obviously the weight of the door is pulling it down, so that will be pushing it against that slot. So both at H1 and H2 there should be some vertical component of force. So the weight of the door is acting through the center of mass. So this will create some vertical component of reaction force at the two hinges. So I'll call this, let's say, R1, and this as R prime, or this is vertical component. So let's just call this R's vertical component and R prime's vertical component. Okay. But can these forces keep the body in equilibrium? Just think about this. If I assume only two vertical reaction forces are acting, they can balance the weight together, no problem that. But can this keep the body in equilibrium?
No, sir.
Why not? Because equilibrium के लिए क्या होना चाहिए? Not only net force should be zero, but torque should also be zero, no?
Yes.
So this arrangement of forces, can it make the torque zero? No, no. There is no axis about which you can see the net torque will become zero, because they are like, if you choose the center of mass axis, these two are creating clockwise torque and nothing to balance it. If you select this point, then again you'll see that both the R's are not creating torque, but mg is creating clockwise torque. Similarly, you select any other randomly selected point also, you'll see that you cannot balance the torque with this combination. And moreover, torque has to be zero about any axis, not just some arbitrary axis. So about the center of mass, you can see torque is not becoming zero. So if that is the case, there has to be some other component of the reaction force. So there has to be a horizontal component. So now think carefully and tell me what is the direction of horizontal component for R and R prime. R is the reaction force at H1 and R prime is the reaction force at H2. Is it towards the right or is it towards the left?
Sir, left.
Sir, left.
For which one? H1?
Yes.
Yes, that's correct. Because very good. So because see what is happening about the center of mass, these two reaction forces vertical components, it's creating a sense of torque like this. So the door is actually pulling on this hinge H1. On the hinge H1, the door is pulling in this side. There's a tendency to move away from the hinge. So the hinge will react by applying a reaction force that is pulling it back. And similarly, because of the tendency to rotate like this, the door is actually pushing against the second hinge. नीचे वाले hinge H2 पे, the door is actually pushing against it like this. So the hinge will react by applying a opposite force like this. So this one will have a horizontal component towards the right, and this one, as you correctly said, will have a horizontal component towards the left. Okay, so this is my force diagram. So this is complete now. Is there any other force? It's complete now?
Yes.
Okay, so now see, I have to make use of this thing, that the reaction force has the same magnitude. So what does this statement mean? If the reaction force has the same magnitude, R acting at H1 should have the same magnitude as R prime acting at H2. So R can be written as square root of Rx square plus Ry square is equal to square root of Rx prime square plus Ry prime square. So this is like the first equation. So this is one equation. Okay. Then the other equation is net force is 0. So net force is 0 will in fact give me two equations. Along the horizontal, forces have to balance. So Rx has to balance Rx prime. Along the vertical, forces have to balance. So Ry plus Ry prime should be equal to mg. That's my third equation. And now see, I have unknowns Rx, Rx prime, Ry, Ry prime. So I need one more equation. So that will come from net torque being 0. Okay. Now again, I will ask you to think about this carefully, that what point I should take, which will give me the most easy equation to balance the torque. I'm not obliged to take the center of mass axis. I can take any axis of choice, remember, because this is a body in equilibrium. So which point or which points I can choose?
Sir, hinge one.
Yes, very good. If you take one of the hinges, then you'll see that not only the reaction forces at that hinge, but one more reaction force will also not give torque, because the vertical reaction force is acting through this line. So if I take this point where H1 is located, not only Rx and Ry will not be considered for torque, even Ry prime will not be considered, isn't it?
Yes, sir.
Because it's passing through that point. So then only two forces are considered.
Momentum may be 0. No?
So momentum will be 0 for Ry prime also. If I take H1, okay. So then you'll only have to consider the two forces, the weight acting through the center of mass and the Rx prime acting through H2. If I'm taking H1 as the axis. Similarly, I can take H2 as the axis also. Then I have to consider only Rx and mg. Understood this now?
Yes.
Okay, so now write the torque equation correctly. Okay. See, the distances and all are given above in the diagram. 6 feet, then 1.5 feet is the width, and that distance d from each corner is 1 foot. So just use that to write the torque equation correctly. If you finish this off, I'll help you out with the final equation, and then after this we will come to question number 63. In between also there are a couple of questions I want to discuss about angular momentum conservation questions. I'll discuss. Okay. Okay, so hope you have written the equations. So I'll just put it out here. So we'll take about, let's say, about the hinge at H1. We'll take net torque as 0. So about that hinge H1, we will just have to consider this force, Rx prime. Okay. So for that, this will become the moment arm. So this moment arm will be how much? L minus 2D. Okay. And of course, we'll have to consider the weight. And for the weight, the moment arm will become this distance, which is B by 2. Okay. So weight is creating clockwise torque. Okay. And Rx prime, you can see, is creating the anti-clockwise torque. So this is going to be balanced by this. Okay. So Rx prime into its moment arm, which is L minus 2D, has to be balanced by the weight multiplied by its moment arm, which is B by 2. So now let's substitute. So Rx prime into, what will this become? 6 feet was the length. No? So 6 minus 2, 4. And this side, the weight was how much now? 8 kg, so 80 newtons. And B was 1.5. So 8g into 1.5 by 2. So Rx prime is, so this is my third equation. Sorry, my fourth equation. So Rx prime is becoming how much now? It is becoming 8 into 1.5, that is 12 g divided by 4 into 2, 6. So Rx prime is becoming 2g or 20 newtons, let's say. We're taking g as 10. So now from above, we can see that Rx is equal to Rx prime is equal to 20 newtons. Okay, that's one thing. Now we can also see that from equation 1, if you just square that, okay, Rx square plus Ry square is equal to Rx prime square plus Ry prime square. So the fact that Rx is equal to Ry, if you substitute that here, it will mean that Ry is equal to Ry prime. Okay. So that also means from equation 3, Ry plus Ry prime is equal to mg. So Ry is equal to Ry prime is equal to half of mg, which is 4g, 40 newtons. Okay. So the reaction forces are square root of horizontal component square plus vertical component square. So 2g root 5. Which one, Jay, should be 15?
Rx prime.
Rx prime should be 15, is it? Okay, let me just check. Rx prime into the moment arm, which is 4, is 8g, which is a weight, into 1.5 by 2, no? Oh, yes, correct. So I made some calculation mistake. So this is not coming as this. Correct. So it's 1.5. That is 15 meters. Correct. Okay. So this should be okay, and this is correct, no? Yeah. So now
Yes, sir.
just correction. Anyway, this will be a bit of a tricky calculation. Just leave it this way only. Okay, anyway, hope this question is clear now, people.
Yes, sir. Clear.
Okay. So next question, Harsh, you have asked us question 63. So I'll come to that. Before that, yeah, there's a collision problem, very good one. Before that, just couple of questions of angular momentum conservation in general I want to discuss.
Sir, can you scroll up?
Yeah, sure. Okay, finish with this.
Sir, take down. Sir, done.
Done. Okay, now we'll discuss a couple of questions here. Question number 54. Okay, it's a very easy question. You just need to discuss it. It's not so much. So just go through the language of question 54 if you have the book. Otherwise, I'll explain the question in a moment. If you have the book, just go through the language of the question. And if you haven't seen the question before, try to understand what the question is saying. Okay, so the question says that there's a boy standing on a platform which is free to rotate about its axis. The boy holds an umbrella in his hand and the axis of the umbrella coincides with that of the platform. Moment of inertia of the platform plus the boy as a system is given and that of the umbrella is given. Okay, the boy starts spinning the umbrella about the axis. So find the angular velocity imparted to the platform. So just assume the platform is like a flat horizontal disc kind of shape. And while it is resting on the floor, but there is some mechanism by which it can rotate freely about this axis. And the boy is standing on it with the umbrella in his hand. So initially the system is at rest. So the initial angular momentum of the system is how much? It is 0. Now to make the umbrella start rotating, now suppose he starts making the umbrella spin in this direction. So how the umbrella will get angular momentum? He would have only applied torque over some time now. So the boy would have applied torque, which imparts angular impulse on the umbrella. So by action-reaction principle, the umbrella's surface will apply an equal and opposite force and therefore equal and opposite torque on his body, which will give his body plus the platform as a system, because there's no slipping between them, a reverse angular speed. So if this gets an angular speed omega-1, this will get an angular velocity omega-2, which is opposite in direction. Omega-1 is opposite in sense to omega-2. Is this concept clear, people?
Yes, sir.
So this is basically the rotational equivalent of that thing we had seen in center of mass. Let's suppose a boy is standing on a platform on a frictionless surface. Now, if he throws something horizontally by applying some impulse on that object, the object will apply equal and opposite impulse on him. So if the object starts moving with some velocity v1, the boy plus the platform will start moving with a backward velocity v2, so that the momentum of the system remains conserved. It remains 0. So same thing will happen here. So basically, angular momentum of the system will remain conserved, okay, and equal to 0. So therefore, the angular momentum of the umbrella should be equal and opposite to the angular momentum of the boy plus the platform. So moment of inertia of the umbrella into the angular velocity which he is given to this. Magnitude wise, they are the same. The minus sign won't come in the magnitude. Will be equal to moment of inertia of the boy plus moment of inertia of the platform as a system into omega. So this is of the umbrella. This is for the boy and platform. So this is this type of angular momentum conservation question. So there are a few more questions in this entire series. So make sure you work them out later. Okay, they're essential for your understanding of concept of angular momentum. So this was question number 54. There is this whole series of questions 52, 53, 54, right up to about 57, 58 in fact. Okay. So these questions 52 to 57, about 5 questions.
Can you explain that how that in angular momentum is conserved? Once again.
See, what is the condition beta for angular momentum to be conserved? How we know that?
Sir,
When do we
net
conserve linear
torque
momentum?
equal to 0.
But for a system, is it just enough to say torque is equal to 0? Or what type of torque should be 0? Net external, no?
Yes.
So just like in the side one that I've drawn, the person on the platform. See, there is force that he applies on the ball when he throws it, but the ball applies an equal and opposite reaction force on it. So if you take the person plus the ball as a system, what is the net external force? It's zero, na?
Yes.
So its momentum is conserved. So like that now, if you take the platform plus the boy plus the umbrella as a system, there is no external agent that is applying any torque. ठीक है ना?
हाँ sir.
अगर उसका axis free नहीं होता, like suppose there was friction on the ground, so then the moment there's a tendency for the platform to rotate, the friction would create an external torque and prevent the platform from rotating. But here it's a free axle, na? So we have to assume the ground is frictionless and it's a fixed free axle. So the platform plus the boy together are free to rotate. The umbrella can be rotated by the boy in his hand, but the whole thing as a system, there is no external torque. Whatever torque the boy applies on the umbrella, equal and opposite reaction torque the umbrella applies on it. So as a system, the net external torque becomes zero. So angular momentum is conserved, and initially it was zero, so it will remain zero.
Yes sir.
Okay, understood. Okay, so these questions, please try them out later. 52 to 57, you can use this question as a guideline. The same concept is there everywhere. Conservation of angular momentum. Now, angular impulse concept. So that is, we'll discuss question 59, and then we will come to your doubt, question number 63, Harsh, after this. Okay. So once again, just go through the language of question number 59. Try to make a diagram and understand it properly yourself. If you haven't done this question before, just try it out. Okay, let's move on to question 59. So it says that we have a uniform rod. It is struck at the end by a force perpendicular to the rod for a short interval. So nothing else is given. So you will have to assume that the rod is lying on a frictionless horizontal surface. And of course, it's not hinged or anything like that. It's a free body. So this is on a smooth horizontal surface and gravity is going into the plane and it's initially at rest. And now you're striking it with a sharp force at one end, acting for a short duration of time t, perpendicular to the length of the rod. So basically, you are applying a sharp impulse j, which is equal to f into t. That is the meaning of the question here. The direction of the force is perpendicular to the length of the rod. It's acting through the end point. So what will happen as a result of this? The rod will start moving in that way that it has both translation and rotation. So the center of mass of the rod will develop a linear momentum in the direction of the linear impulse. J is equal to delta p, that concept. And also this linear impulse is having a moment arm with respect to the center of mass. So it will generate an angular impulse and the rod will develop a torque. So linear impulse is equal to change in linear momentum, which will in this case become mvc. And angular impulse, that is r cross j, that will become your tau delta t kind of thing. So this is the net angular impulse that should be equal to change in angular momentum. That should become I omega. So just use these two equations to find out all the quantities which are required. And we are going to work out this last part. Or let's work out the C and D part. The kinetic energy of the rod after the impulse is active and the angular momentum of the rod about its center of mass. Okay, so you can see here that the force equation or the linear impulse equation will be this. So Ft is equal to mvc. So from this, the velocity of the center of mass is linear impulse force into time divided by mass. And this equation R cross J is equal to I omega. This will tell us that L by 2 into Ft, which is creating an anti-clockwise angular impulse, will be ml square by 12 into omega, which will be anti-clockwise. So the angular speed of the rod about its own center of mass immediately after this will be 6 Ft by ml. And the angular momentum about the center of mass, that will be having a magnitude of ml square by 12 into 6 Ft by ml, or that is the same thing as actually L by 2 into Ft. And the sense of it is anti-clockwise. So now all this is done. Okay, so now only one thing, the kinetic energy will be the kinetic energy of translation plus the kinetic energy of rotation. So this will be the kinetic energy.
Sir, you have found that torque and then you multiplied by time. No?
Yeah, I mean, it's more like we have calculated, we know the linear impulse now. So we have taken the moment of linear impulse is angular impulse.
Yes. Angular impulse equal to linear impulse into momentum.
Correct, that equation. Okay, so hope this is clear. Now next we'll go through question 63. We just go through the language of the question. So we'll apply the same type of concepts there, conservation of angular momentum, conservation of linear momentum or whatever. But it is in context of a collision occurring. Okay, so we'll also have to take that into account. Okay, so people, let's go through the 63rd question. So you have these two particles which are joined by a light but rigid rod. System is initially translating on a frictionless surface. Okay. And now another particle P, the same mass is at rest on the surface, sticks to the ball B as the ball collides with it. Okay. So this is one of the questions that you have asked as a doubt, Harsh. So this is the situation. These are your two particles, identical particles A and B. And this whole system is translating on the smooth horizontal surface, both of them with a uniform velocity V0. Now imagine there's another particle which is at rest on the ground over here of same mass M. And what happens is that when A comes and collides with it, that particle sticks to A. So let's say after a bit of time, what we observe that this rod along with the two particles has just about reached here. And
inelastic collision.
It's a perfectly inelastic collision because they're sticking together. Coefficient of restitution will be 0. Okay. So what do you think will happen after this collision? Will the system continue to move in like in translational motion like this? This is pure translation, no?
Sir, it will rotate.
Yes, it will rotate. Okay. So it will rotate about which point now? What will be the natural axis of rotation?
Sir, center of mass.
And where will the center of mass be? Remember, this has become 2m now, no? So the new center of mass will be here. It won't be the midpoint of the rod anymore. Okay. So about this, there will be some rotation with angular speed omega. Will it be like this or will it be the other way? How do you think the angular speed should be?
Sir, anti-clockwise.
It should be clockwise, because the particle P will apply an impulse on A towards the left. No? So that will tend to give it a sense of rotation, which will be like this. But at the same time, the system will also have linear momentum. So the center of mass will be traveling with VCM. So what we'll do is we'll look at the system just before impact. So just before impact, this is still in pure translation. V0 and V0. Yeah, and this one is at rest, the particle P. So we'll take A plus B plus the particle P plus the rod as our system. So there'll be conservation of linear momentum because there's no external force or external impulse. So equation of conservation of linear momentum before impact, how much it is? A and B are both moving with V, so 2m V0 horizontally. After impact, what is happening? The whole system has a net mass of 3m and its center of mass is traveling at a velocity v. So this is our first step. Okay. And conservation of angular momentum. Now again, this conservation of angular momentum can be done about any axis of choice. So I'll show you two convenient axes over here. About any axis of choice. One is we will do the conservation of angular momentum about C. That is the center of mass of the whole system. So in this picture, in the picture before collision, just before impact, this is where the center of mass is. Now, by the way, where is the center of mass in terms of distance? You can figure this out. Here we have a mass of 2m on this side. And on that side, we have a mass of m. So the center of mass will divide this line is in 1:2 ratio. So that distance d will be 1/3 of L. So D is L by 3. Okay. Now before impact, this is acting like a rigid body which is traveling with the speed v0, but the angular speed is 0. So remember, formula for angular momentum about an arbitrary point. It is what? Angular momentum about any arbitrary point is RCM cross MBCM plus ICM into omega. Right? This equation is clear now?
Yes.
Okay. So now see
Sir, but
this
about which point you are taking?
about the new center of mass. Now I'm going to take. So I'm going to take the angular momentum of the rod about this new center. Okay. So this is of A plus B as a system. So A plus B as a system, its own center of mass is actually where at O. So where is the center of mass located? It's located at a distance of L by 2 minus L by 3. So that is L by 6. And the linear momentum is 2mv0 in magnitude. So this angular momentum about C will have a magnitude of how much? Linear momentum, that is 2mv0 into the moment arm, which is L by 6. And that sense is clockwise. And the other particle P is at rest. So it does not have any angular momentum. So it's 0 for the particle P. This is for the particle A plus P. This is the angular momentum for the system about C before impact. This is before impact. This is clear?
Yes, sir.
Okay. Now what is the angular momentum about C after impact? After impact,
Sir, you have taken A plus B as a system in
A plus B plus A plus B plus P as a system. Okay. So in the before impact case, now A plus B is like one rigid body, right? And P is an independent particle.
Yes.
So that rigid body has how much angular momentum about C? It has R cross MBCM because it's not rotating, it's only translating. Okay.
Yes.
And the particle is 0 because it's at rest. So the total system, that is A plus B plus P plus the rod as a system, has how much angular momentum? R cross MB for the rigid body and 0 for the particle. Is it clear?
Yes.
Okay. Now see, after impact, the whole thing is one rigid body. No? The whole system of A plus B plus P is stuck to B. So it's one system, one rigid body whose own center of mass is translating with VCM, but also has angular speed omega about the center of mass. So about its own center of mass, how much will be the angular momentum? Moment of inertia about center of mass into omega, right?
Yes, sir.
Okay, now what will be the IC after impact? It will be, you have 2m, that is A plus P at a distance of D, which is L by 3 whole square, plus you have the single particle M, which is B above, at a distance of 2L by 3 above. So it is ml square, 2 by 9 plus 4 by 9. So 6 by 9 or 2 by 3 ml square. Just check my calculation, is this correct?
Yes, sir.
Okay, so after impact, how much is the angular momentum about C? It is 2 by 3 ml square omega, and you can see it is, it is clockwise. So conservation of angular momentum about C, that will be initial angular momentum, which you've written above, 2mv0 into L by 6 clockwise. And after impact, it is becoming I omega, that is 2 ml square by 3 into omega. So this will give us the value of omega. You can see this is v0 by 2l. Is that correct?
Yes, sir. Correct.
Okay. So I will show you the conservation of angular momentum about another axis also. This might not be the most convenient axis. Okay. However, it's quite convenient actually. I think this is quite fine actually. but we have another option also, so we'll discuss about that for conservation of angular momentum. But if we go with this option of conserving angular momentum about the new center of mass of the system after impact, then this is how we solve it, and this is the angular speed that we're getting. Okay, so just make a note of this, and next we will write the angular momentum conservation equation. So you can see the first equation is independently giving us the value of VCM. It's nothing to do with the second equation. The second equation is for omega, the first equation is for VCM. And this directly gives us VCM as how much? 2 by 3 V naught. So yeah, beta. Okay. Now there is also an E part of this question where we have to calculate the linear speed of A and B just after impact. So we'll discuss that also. But actually you have to first find the VCM and omega. Only from that you can get the linear speed. Because it will be a combination of VCM and for B that is above, you can see the linear speed will become VCM plus L by 2 omega, because omega is clockwise. Okay? And for A plus P below, it will be VCM minus L by 2 omega, right?
Yes.
Okay. So that part you can complete yourself, but just first understand the conservation of angular momentum part. Now we will also conserve the angular momentum. Instead of this, we will conserve it about O. That will also be an interesting way of solving the question. Okay. So next we will conserve angular momentum about O, which is the midpoint of AB. That is another nice option to solve this problem. Conserve the angular momentum about O, which is basically the midpoint of the rod. Okay, so if you've finished with this, let's also see how we can conserve angular momentum about the midpoint of the rod next. Okay, so we look at the whole system again, before and after impact. So this is just before impact, and let's say this is just after impact. So just before impact, P is at rest. A is moving with velocity V naught. B is moving with velocity V naught. And this is the point we are considering, the midpoint. Okay. And just after impact, what we saw is that this combination of objects, which is like now a combined combined mass 2m at the bottom, that is A plus B, sorry, A plus P, and this mass B at the top M. These are all M. So they are moving in such a way that the center of mass of the system has a velocity VCM, and about this there is an angular velocity omega. So now, in reference to that center of mass, that point O is here. So this distance is L by 3. So this distance is L by 6. Okay. Now we already had the equation that 2m V naught is equal to 3m VCM. So we already know the value of VCM from equation 1. It is 2 by 3 V naught. Okay, because we'll require that now. Now in the first picture, what is the angular momentum of the system about O? You can see that this is the center of mass of the rigid body, and the rigid body is not rotating. So rigid body is O, 0. A plus B as a system has 0 angular momentum. And of course, the particle P also has 0 angular momentum. So it's 0. And in this diagram, how much is the angular momentum about the point O? It will come from that formula R cross MB plus I omega. So R cross MB will be what? It will be L by 6 into the total mass 3m into VCM. And you can see that, with respect to this point O, the center of mass sitting here is moving with a velocity VCM like this. So it is having what sense of angular momentum? It is having, okay, anti-clockwise sense of angular momentum. Okay, and plus ICM omega, but that ICM omega will come with a minus sign because the omega about the center of mass we have seen is this. Okay. So this is after. And this is before. Okay. So since the angular momentum is conserved, we will write 3m VCM into L by 6 equal in magnitude to ICM omega. And then we'll just borrow this value of VCM here. So this is m into VCM, which is 2 by 3 V naught. L by 2, this will become 3 and 6 cancels. Okay. And on that side, ICM we had seen already was 2m into L by 3 whole square plus m into L by 2L by 3 whole square. So that had come out to be 2 by 3 ml square. So this is giving us omega equal to how much? V naught by 2L. This is also fairly easy. Any other point you take will be a little bit more complicated, but because it will involve both the terms VCM and omega and V naught. All three terms it will involve. Whereas this was involving only VCM and omega. The earlier one was involving only V naught and omega. So out of the three terms, only two are getting involved in each of these choices of axis. Okay, so hope this is clear. And now the first part of the question actually, just after impact, the velocity of the point B or the particle B will become VCM plus the distance of that point. So the distance from C to B is actually L by 6 plus L by 2. Okay, so that is how much? 4 by 6, so 2 by 3L. Of course, and the distance from A to C is L by 3. So VCM plus 2L by 3 omega. Okay, so that is 2 by 3 V naught plus 2L by 3 into V naught by 2L. So that is, in fact, interestingly, V naught. The velocity of the point B is coming out to be V naught, whereas the velocity of the particle A will come out to be VCM minus L by 3 omega. So 2 by 3 V naught minus, sorry?
Sir, not understood that how you come VB and VA.
VB and VA, okay, I'll explain. See, any rigid body, forget about this one alone. If its center of mass is moving like this, okay, and there is angular velocity omega about center of mass. And now we talk about any general point P inside, which is at a position vector r with respect to the center of mass. So what is the velocity of the point P with respect to the center of mass? It is omega cross r, the circular motion velocity, right? So what is the
Yes.
velocity of respect to ground? It becomes VCM plus omega cross r. Okay, so this we are now implementing over here. Okay. So see, the center of mass is having a velocity in this direction and the omega is in this direction. So this particle B here, it will have a velocity with respect to the center of mass in the forward direction because omega is carrying it like that. So that will be, this distance is how much? It is L by 2L by 3. Sorry. So it will be omega into 2L by 3. But plus what is happening? The center of mass is moving in the same direction. Huh? So plus VCM. Got it now?
Yes, sir.
Like in rolling also we saw, no, the highest point has a velocity of 2 VCM. How that happens? Because it's VCM plus R omega. No, and the lowest point has 0. But here it's not 0 and 2 V naught, but it's some combination
Yes.
of that. Okay. Clear now? Okay. So this term will give me how much? It will give me 2 by 3 minus 1 by 6. So that will become how much? 3 by 6 or 1 by 2. No? So A's velocity should be V naught by 2 in the forward direction. B's velocity should be V naught in the forward direction just after impact. Okay, so I'll just minimize this a little because this thing is also important. How we did the angular momentum conservation about the point O, which is the midpoint of the rod, instead of about the system center of mass after impact. So this is another nice option you can apply with. Yeah. So just go through this question. Next, we'll be discussing question number 66. It's also an important question. So 66 we can do by two options actually. We can use work by energy or we can use dynamics, that is torque, force, etc. So all these options are there. Okay, so hope this question is clear.
Sir, 1 minute.
Okay. In the meantime, just go through question 66. All of you will discuss.
Sir, done.
Okay. So question 66 has a rotating pulley and a spring mass system. Some kind of axle here. So we have a massless thread which on one side is connected to a spring and the other side it is attached to a block. In the spring's other end it is connected to the ground. So this is the situation given to us. Okay. So radius of the pulley is also given. Okay. Moment of inertia of the pulley is given in kilogram meters square. String going up attached to a spring of given constant supports 1 kg block. The system is released from rest when the spring is at its natural length. So when we release the system, at that moment, what is happening? Initial velocity of the block is 0 and x is 0 for the spring. So immediately when we release it, what will happen? At that moment, the tension in the spring thread will be 0 because the tension in the spring is 0. So it will have an initial acceleration equal to g. But now after some time, as the block has gone down, it has pulled the thread. So first of all, the thread would have made the pulley also rotate. Okay. So while the initial velocity of this is 0, so the angular speed of this also would have been 0. So this is at t equal to 0. But now after some time at t, the block has gone down through a distance of x, let's say. So the spring also has got stretched L plus x, increased from its natural length. This was L. So at this stage, the block has an acceleration A, a speed V. Okay. This has an angular speed omega and an angular acceleration alpha. And also this side of the thread has a tension T1. This side of the thread has a different tension T2. Okay. So if you think dynamically, T2 is equal to Kx, because this is a massless point over here where the thread is attached to the spring. Then T1 minus T2 into R is the net torque. So that is equal to I alpha for the pulley. Okay. And mg minus T1 is equal to ma for the block. And A is equal to R alpha, no slipping condition. So these are the equations if we want to go with the force method. So we have to, but however, we don't have to actually go by the force method. We can also apply the work energy method. So you know that here, elastic potential energy of the spring plus gravitational potential energy of the block plus kinetic energy of the block plus kinetic energy of the pulley will be conserved. Because there's no external force doing work on the system and there's no non-conservative force. Okay, because work done by external forces is zero. External force is basically the force acting through the hinge, which is not doing any work. And there is no kinetic friction. There is friction between the pulley surface and the thread, but that is static friction. It's not allowing slipping to occur. So work done by non-conservative forces is also zero. So total mechanical energy is conserved. So if I'm conserving total mechanical energy, I can see this way that the blocks, the spring's potential energy has increased by half kx square. Okay. The gravitational potential energy of the block has gone down by mgx because it's gone down by the same distance x. Block speed has become half mv. I mean, kinetic energy has become half mv square, and the pulley's rotational kinetic energy has become half I omega square. So this is the change in potential energy of the spring plus change in gravitational potential energy plus change in kinetic energy of the block plus change in kinetic energy of the pulley. So this combination is zero. So this is like this, and of course in this V is equal to R omega. This is the no slipping condition. So when you substitute that, you can see here that you can write it like this: half mv square 1 plus I by mr square it will become. Where m is the mass of the block, I is moment of inertia of the pulley, r is the radius of the pulley. And on the other side, if you take these terms, this is mgx minus half kx square. So from this, in general, you can find v at any given x. But for example, you can also find that what is the maximum x. The maximum value of x will be when kinetic energy is zero. So v is zero. Okay. Whereas, so like that, you can do that type of analysis in this question also. Okay, so hope this question is clear.
Yes, sir, clear.
Okay, okay. Just take this down, and I want to discuss a question in rolling before we measure.
Sir, done. Okay, now remaining questions in HC Verma are like quite basic rolling questions. I think you'll be able to finish most of them yourself without too much difficulty. I want to discuss a couple of different questions in rolling. In any case, the doubts are done, so just want to discuss a couple of important types of situations in rolling. So this is a rough surface, a rough horizontal surface, which has a coefficient of friction mu. Let's say that coefficient of friction is 0.2. Now what we do is we take a solid sphere and give it some spin and place it on the surface. So initially at t equal to 0, the solid sphere has only got an angular spin but its linear velocity of the center of mass is 0. So a spinning ball, which is in the shape of a solid sphere, let's say mass 1 kg, radius equal to 20 centimeter. Okay. Initial angular speed is, let's say, 20 radians per second. Okay. So the spinning ball is placed on a rough surface at t equal to 0, as shown. So first thing we'll do here is we'll understand from the free body diagram what is the linear acceleration and angular acceleration it will develop. So draw its FBD and determine the acceleration of its center of mass and the angular acceleration about its center of mass. Okay. Then find out after how much time it rolls without slipping. And find the speed when it starts rolling. Find its velocity of center of mass in the rolling without slipping situation. Okay, also take G as 10 meters per second square. So first of all, try to understand how friction will act to prevent slipping, and also a hint to you that friction will act for a limited amount of time. So try to figure out why that's happening.
Sir,
Yes.
sir, if G is not then given, then what we have to take? 9.8. No?
In HC Verma, you have to take 9.8 always. Yeah.
Sir, no, I was asking in exam.
In exam, though, it will be given. Because what happens in the first page, before you actually start the exam, there's an instruction time of 15 minutes and all that stuff. So the values of all the important constants are given.
Okay. Sir.
Okay, so what will be the direction in which friction acts when we place this ball on the surface? स्लिपिंग किस डायरेक्शन में हो रहा है? At the point of contact, is it to the right or towards the left? See, if this wall is
right.
Friction is towards the right.
No sir, friction is toward left.
नहीं बेटा, see r omega at the point of contact कैसे है? Towards the left or towards the right? V equal to r omega na. So this object is spinning like this. So where is this point of contact slipping? Towards the back na. You're following?
Yes sir.
So a spinning object like this point will have a velocity in this direction because of that omega. So friction has to act opposite that na. So immediately friction will start acting like this. The moment you place it in contact, and this will be which type of friction? It will be kinetic friction because there's actually slipping occurring. So this will be kinetic friction equal to mu n. But at the same time, there's also normal reaction acting vertically at this point. And there is mg acting through the center of mass. So now you can see now mg and normal reaction cancel each other. So there's no net force because of them. But also they're not creating any torque. But friction is creating both translation and rotation. So because of friction, the center of mass has a forward linear acceleration like this. And it's also creating a torque like this. So there's an alpha because of friction. Okay. So net force is equal to mass into acceleration. You can see normal reaction is mg. So kinetic friction is ma. Okay. So mu n is equal to ma. So this will tell me that the acceleration of the center of mass is mu g. Okay. Now also torque is equal to I alpha about center of mass will take. So kinetic friction into R is equal to 2/5 mr square alpha. So our alpha will come out to be 5/2 mu g by R in the anti-clockwise sense. Whereas omega, remember, was in the clockwise sense. Okay, this is clear?
Yes sir.
Okay, so now because of this linear acceleration and this angular deceleration, ACM and alpha like this, whereas initially it was spinning like this. So what will happen is that after some time, the center of mass has developed some velocity VCM and the angular velocity omega. So this is at time t, this was at t equal to 0. So at t equal to t, the linear velocity of the center of mass is ACM into time because its initial velocity was 0. So it is mu g into t. Whereas the angular velocity will be initial angular velocity, which is clockwise, minus alpha, because alpha is anti-clockwise into t. So omega as a function of time is omega naught minus 5/2 mu g by r into t. So this is v and omega as a function of time. Now what will happen is that at some point of time, let's say t equal to t1, VCM becomes equal to r omega. So the point of contact stops slipping. So what happens at that stage? Because there is no other external force acting, external force or torque, the moment the point of contact stops slipping, friction will stop acting because there is no slipping anymore and there's no tendency to slip anymore also. So if friction continues acting, then it will unnecessarily increase the omega more than required. Sorry, increase the VCM more than required, and again it will start slipping. So the moment this happens, friction ceases. Because there's no slipping, so there's no kinetic friction acting anymore. And the body continues in pure rolling, that is without slipping. Okay, so this is the most important aspect of this question. Hope this is clear.
Yes sir.
Okay, so how we'll find that time and how we'll find that, so numerically you'll see this mu g was coming out to be 2 meters per second square, right? And this alpha will therefore come out to be 5 by 2 into 2 divided by what was the radius? The radius was 20 centimeters, so 0.2. So 25 radians per second square. That's what this is coming out to be. So VCM as a function of time is 2t, and omega as a function of time is omega naught, which was, how much was that? 20 radians per second. So 20 minus 25t. Okay. So when rolling starts at this time t1, VCM is equal to R omega, means that at that time, whatever my value of VCM, which is mu g t1, it should be equal to capital R into omega naught minus alpha t. Okay. Or 2t should be equal to 0.2, which is the radius, into omega naught, which is 20 radians per second, minus 25t. So this will give me the value of time, that time t1. 2t1 will be equal to 4 minus 5 t1. So t1 you can see will become 4 by 7 seconds. And at that time, the speed of the center of mass will become therefore 8 by 7 meters per second when the rolling starts. Okay, so this is a very critical type of question. This question is not there directly in HCV, but you will find this type of questions in your module exercises also. Okay, so it's an important type of question. So hope you have understood this properly, people.
Yes, sir.
Okay, so just make a note of this solution. I'll send you the notes also, but just go through it. Let me know if there's any doubt in any of the exercises, and we will discuss. Okay. So that's it for today's session, people. Thanks for attending. Wish you all the best.
Thank you, sir. Bye.